So topic 6 is refrigeration, okay, heat pump and the environment. Okay, the environment part I will not touch too much. Okay, mostly on the two, because it is related to the due to the heat comfort. Okay, what I'm going to cover is the basic principle of heat engine, heat pump, refrigeration, and air conditioning. So this 4. Then the refrigeration cycles, basically a cycle of heat pump, refrigeration, and air conditioning. So understanding the thermodynamic behind those cycles, type of refrigerants, and then we do some of the solve example here. Okay. So what is refrigeration? So you have fridge at home, you have aircon at home, you have aircon in your car. So all those are refrigerator. Okay, more or less. So it's a process of removing heat. Okay. Okay. For example, you see here, this is different unit of refrigeration. So we remove heat from environment here. This is probably the fridge. Okay, the freezer on the top of your fridge, first there, and this is the one in the middle and the one at the bottom. So basically, what we do in refrigeration here is we take heat. What is the simple word of taking heat? When we take heat, we make it cold. Okay, so if you want to make cold of the space inside, so basically we are making the space inside the fridge colder by taking heat. Okay, so that's the thing. We are taking heat, and so because heat you cannot contain it, so you take it continuously, and then we bring it outside. Okay, so when refrigeration, air conditioning, heat pump, the 3 things is basically the way to remove heat from one place to another place. So that's the thing. So your mind always think that, okay, refrigeration is to remove heat from one place to another, or refrigeration, heat pump, and aircon is to remove heat. Okay. So the lot of application. Okay, domestic, in your home, you get fridge, freezers. Fridge is the one in the middle and down. Freezer is the one normally in the top. That's to make ice. Okay. In transportation, okay, this is to transport the food. Okay, frozen food. Okay, that's use refrigerator. In industrial, we need to sterilize your milk. This is in Europe. The brewing. You make ice cream, all need temperature below 0 degrees Celsius. In commercial, we see it in the freezing section. You want to buy the frozen food, you see that one. It is in the hotel, in the restaurant. Restaurant also, we need to store food. We need to have a cold drink. We need to store lot of the vegetables and so on. Air conditioning in hospitals, offices, FIT, in aeroplane, we have conditioning in the train, cars, as we mentioned here, laser sport, ice rinks, and so on. So basically, modern human being cannot be too far from refrigeration and air conditioning. So it's really part of us. We are privileged here. If you remember last 2 weeks, when we discussed about how much energy used in Brunei, okay, 80% of the electricity is used for fridge and aircon. 80%, 80%, a lot. Okay, so it is then makes sense why we learn that one in this modules. Okay, now we look into the air conditioning. So what we do is basically we take heat from the room. You see here Q2. Okay, we take heat, okay, from a cold room. For example, you are now sitting in a room at 25, and then you try to take heat from the cold room and then throw it away outside. Okay, here you throw it away, you bring it in, and then you throw it here outside at higher temperature. Okay, basically it doesn't really follow the thermodynamics, right? So basically, how come you can throw away heat from a cool room to from the colder space to the hotter space? So yeah, so it doesn't come naturally, and then we will learn about the cycle later on. So it doesn't come naturally, but the concept is that the same. So the basic idea is when we evaporate a liquid, for example, it's happened here, evaporator. Okay, when we evaporate the liquid, we need heat. So that is how we take away heat from the room. We evaporate a liquid somewhere it happened in your the aircon box. So aircon box mainly consists of an evaporator. That evaporator, okay, you have a refrigerant, call it, the liquid is called refrigerant inside. The refrigerant evaporate, change the condition from liquid to vapor. So when it's changed the condition from liquid to vapor, it's absorb heat. Conversely, outside of your house, you have a condenser unit. In condenser unit, so what happened there is, what happened here is that your vapor, okay, your vapor, the gas, condense to become liquid. When it's condensed to become liquid, it's release heat. So basically, if you repeat again, you take in the heat, absorb heat, release heat, it has become a cycle. Okay, then we call that a refrigeration cycle later on. So from the, okay, in the case of air conditioning, from the cold room, you absorb heat, and then by evaporating a liquid, a refrigerant liquid, and then outside of the room, you condense it by releasing the heat. Okay, absorbing heat, evaporation, releasing heat by condensing. Those are the cycle. So this is a graphical example of room. You can have also a graphical example here in the car. So in the car, you want the inner part of the car to be cold, right? So you need to take out the heat from your car. So taking out the heat can be done by evaporation. So in this unit, in this car, this is basically evaporator. Somewhere, okay, inside your car, there is an evaporator. When the liquid evaporate, then the liquid will be pumped out outside of your car, okay, and it's condensed to release the heat. So exactly the same cycle. It's the same cycle in for the aircon in your room, for the aircon in your car, and also for the fridge and freezer in your refrigerator. All give the same principles. Okay, so next, now we'll learn the thermodynamics. So what happened? So before we discuss about heat pump and heat engine, refrigerators, and so on, let's go back and look into what happened to your car engine. Car engine work. It's called as heat engine. So what is heat engine? Heat engine is an engine that convert hot reservoir. Hot reservoir is the one inside the combustion, the gas. Okay, you have a combustion gas in the machine. Okay, it's become a hot gas. That hot gas is used to rotate your engine, your wheel. Okay, that is basically you produce work and the car move. Okay, and then it's released to the X house. So we call it cold reservoir. This is the thermodynamic illustration of heat engine. So we take out from the heat, we take part of the heat to become the work. Yeah, work is the car moving. That's the work. And we leave some of the heat, we release some of the heat to the environment. So when we have this kind of mechanism, okay, so basically what we get is work. So we can come up with a term of efficiency. So remember, efficiency is when you have 100% efficiency. What does that mean? That is mean we use all of the heat here to produce work. That is 100% efficiency, right? So basically you can convert all of the heat to produce work. That is 100% efficiency. But in the reality, it is impossible to get 100% efficiency. Okay, you can only get certain efficiency in heat engine. And then the way to represent it, the efficiency then is any work that we get, any power that we get from the engine divided by the QH. QH is the one here, the heat from the reservoir. That is efficiency. Okay, and then we do the balance. We know that QH here equal to work plus QC. Oh, so work here equal to QH minus QC. Then if you divide it by QH, we get efficiency equal to 1 minus QC over QH. Okay, 1 minus. And then this one. So this is the actual efficiency of heat engine. I know we will not discuss this one, but we will refer to in many problems later on. So what important now is how much actually we can get maximum. How much work we can get from a heat engine. I will not explain to you. It's called as a Carnot engine. Okay, and then the maximum efficiency we can get is equal to this. So E, okay, efficiency maximum M equal to 1. Okay, it is correspond to 1 minus TC over TH. Okay, this one. 1 minus TC over TH. This is for heat engine. Next, we have a configuration called heat pump. Heat pump is not popular here because we have quite hot climate, but it's very popular when you are in Canada or Russia maybe, or in Europe. So what is heat pump? Okay, in heat pump, heat enters a hot reservoir, so basically QH here, from a cold reservoir. So it's from cold, it's a reverse of the heat engine. It's from cold reservoir. Okay, but this is impossible. How come we move from a cold to hot? Yeah, it is impossible. So it is not, we call it in thermodynamics, it is not spontaneous. It is not spontaneous. Therefore, we need to give some work. Okay, work is basically the electric, for example. The electricity, we bring in work to be able to move heat from cold reservoir to hot reservoir. So you can imagine, for example, outside is the temperature of minus 10 degrees Celsius. Inside the house, the temperature is 20 degrees Celsius. But still, you'll be able to bring in heat from outside to the inside with the help of this guy, with the help of work. Okay, so in this case, you see, the one before, we have efficiency, we have term of efficiency. Now we cannot use efficiency, work over QH. It doesn't really make sense. Remember, we then come up with a term called coefficient of performance, which is COP, the COP, coefficient of performance. So it is easily defined as what we want. In heat pump, we want heat, right? We want heat to go in. So we wanted heat. I'm in Europe, for example. I wanted to heat my house. So I want heat. So then it's the definition of COP is QH over W. QH over W, and this is basically 1 over efficiency. If you look into equation, the one on the left here, it is 1 over efficiency. So the maximum, okay, so the maximum heat that the maximum performance of a heat pump can be represented by 1 over E efficiency maximum. Efficiency maximum is you get it from the Carnot engine. Okay, if you don't get all of this idea, you watch again the video. Okay, I try to be as slow as possible. So we have 2 engines done. Next, we will have another 2 engines. Okay, so the next one is the famous refrigeration. The famous refrigeration. So in refrigeration, we want heat to leave a cool reservoir. What we want is QC. What we want is this. Okay, I want QC as maximum as possible, right? I want to cool my room as cool as possible. I want to cool my freezer as cool as possible. So what we want is basically QC. That's why the coefficient of performance for refrigeration is defined as QC over W. And then if you do all of the math substitution, you will end up with this equation. So we can predict what will be the maximum performance of a refrigerator. So why, sir, we need to do the COP maximum? COP maximum is the way for us to measure how good our refrigerator is. Yeah, how good our refrigerator is. So we'll try to be as close as possible to the COP maximum. Okay, that's the reason why. Okay, this is the refrigeration, and the final engine is aircon. So what's the difference is nothing. Okay, refrigeration and air conditioning is basically the same. It's just different target temperature. So what we want in air condition is we want heat to leave the room. Okay, you want heat to leave the room. So the definition of coefficient of performance is exactly the same as the one in the refrigeration. Okay, so this is how it works. So remember, in the case of refrigeration, okay, I'll use this one is okay, aircon. So heat in basically this is the room. This is the room. This is the outside. Yeah. So remember, when it's evaporate here, it's absorb heat, so heat in. When it's condensate, it's release heat, so heat out. Okay. Okay, so this is what happened. It's happened in the cycle. So you have, for example, here, yeah. Normally here I will say it's 0.1. This example. Okay, this 0.1 happened. It's somewhere here. 0.1 is somewhere here. Okay, somewhere here. This is 0.1. Okay, 0.1 we have compressor here. So what happened is that look, it goes up. So this is 0.2. Then this is 0.2. 0.1 and 0.2 different is that now the pressure goes up. Okay. And here, and it go to the 0.3 at this point. So this is 0.3. Okay, at 0.1, okay, 0.1, it's normally okay. I think I will go back. I will explain this one in the next slide. That is 0.3. Go 0.3 here, and then it's go to sorry. Okay, it go to the expansion valve. Okay, at this point, this is 0.4. 0.4 there. So basically there are 4 points, and then we'll spend quite some time to learn about the refrigeration cycle. So you see, this is where we need work. Yeah, this is where we need work. See, work in. Okay, work in here. We need to provide electricity for the compressor. That's it. And then here, just condenser. Here, so this is where the work in. This one where the this is where the Q in. And this is where the Q out. Okay, so to be able to do this cycle, you need to understand this chart. Okay, so this is a refrigeration chart. You need to find out, but I've provided you with a link here. You'll be able to access many of common refrigerant pH chart. What is pH chart? Okay, this is pure thermodynamics. So P stands for pressure. So it's basically the plot between pressure left here and the enthalpy here. Okay, the enthalpy. So the line, straight line from left to right, this one is at constant pressure. Okay, and then you have so where's the, it's not very clear. Okay, you have a different zone here. Okay, this one, okay, this line, it's called saturated liquid. Okay, any zone on the left side, any zone on the left side is, we call it subcooled. This one is sub. Okay, the one on the line here is actually the line of saturated vapor, and anything on the right of the saturated vapor is actually superheated. Okay, the peak of this one is critical point. We call it critical point. Okay, already there. So anything in between the two, okay, in between this one, okay, between liquid and vapor is a mix of liquid and vapor. Okay, and then you have the line here goes up. So basically at this point, for example, so now we have here 10% of vapor, 20%, 30%, 40%, until you have 100% vapor here. Okay, that's mix. Then anything above the critical point, we have supercritical fluid. Okay, so that's the thing, the phase. Okay, the condition of the things, and we have a constant entropy line. Okay, constant entropy line is this. We need this one for compression. So it's normally we have a isentropic compression, so it goes up to this line. So the same line here. So this is isentropic, and then actually we have temperature line. Temperature line is like this one. So okay, this is the temperature. Yeah, this is the temperature. This is the temperature reading. So it goes down, go normally straight from here. So this is at constant temperature. It goes here, okay, goes here, go right here, and go right here. Okay. Okay, you will probably know better when we do the example. Okay, once again, superheated vapor is anything on the right side here. Saturated liquid is on the line here, edge of this line, And then you have saturated vapor is on the another side of the line, on the right side of this line, just on the line, exactly on the line. Subcooled liquid is anything on the left, okay, anything on the left here. Mixture of vapor and liquid is inside, anything in between liquid and vapor. So that's a mixture of liquid and vapor. Supercritical fluid is any point top of critical point. So what is supercritical fluid? It's neither liquid nor a vapor. Something in between. Okay, it's called supercritical. And then critical point is the peak of this point. Okay, that is the basic thermodynamic table. I think it's good enough to start with. So next, we go into refrigeration cycle and chart. Okay, the basic layout is like this one. Okay, remember this one, this line. Okay, I repeat again. This line is for saturated liquid. Okay, until the middle here, and then the second half is saturated vapor. Okay, when we analyze the cycle, point 1, we normally put just before the compressor. So this is compressor. Okay, just before the compressor. So that's point 1 here. And then the typical condition of point 1, so that's the point 1 here. And the typical condition of point 1 is, okay, point 1 is normally saturated vapor. Okay. Okay, the standard condition is saturated vapor. So this point 1. Okay, the condition here is saturated vapor. Or superheated vapor. Okay, so saturated is exactly on this line. When it is superheated, it will go to the right side. To the right side. Okay, that's superheated. So this is superheated vapor. Okay, that's one. And then we do the compression. Compressor is normally isentropic. So what is isentropic mean? It follow this line. It follow this line, isentropic line. You see this line? Okay, that's isentropic. Okay, and you see here it end up with point 2. So what happened at point 2 is basically you increase the pressure. Okay, so this pressure is, for example, this is P1. Now you bring it to P2. That's pressure. It's you increase the pressure. You don't change the thing. So basically here now you can have condition of superheated vapor. Basically, the gas form of the refrigeration that is heated beyond the boiling point. Heated beyond the boiling point. So, okay, that's point 2. So from point 1 to point 2, I will be consistent in using the numeric. Is a compression, okay, using a compressor. Point 2 to point 3 is condensation. So it's not condensation. So condensation normally refer to this point. So it's what we do at this one is to cool, okay, the superheated vapor, bring it to the saturated vapor condition, and then you start to condense it. So part of it become liquid, 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 more liquid, more liquid, more liquid, more liquid, all liquid. So when all become liquid, so this is typical condition is saturated liquid. Okay, saturated liquid. So when 100% is liquid, So that's typical condition, but you can actually bring it more to the right side. Okay, after you condense it, first you cool it down, okay, from 0.2 to somewhere here, saturated liquid. Then you start to condense it, change the phase from vapor to liquid, bring it, and when all become liquid, let's say you want to cool it down. I want to cool it down further the liquid. So you can do it. And then the stage here is subcooled liquid. That's point 2. That's point 3. Point 2 is superheated vapor. And then basically that's it is at P2, and then this is at P3, which is equal to P2. And then what is done next is using a throttle valve, basically sudden expansion. And okay, this one we call it isenthalpic expansion. So because the enthalpy is constant from 0.3 to 0.4, so this one is isenthalpic expansion. Okay, and the typical condition at 0.4 is mix liquid plus vapor. So that's exactly at 0.4 here. And then the condition is, this is at, sorry, this is P1. So this is at P1, so it's a P4, then equal to P1. Okay, so that's the thing. Remember, we changed the condition of the refrigerant. Okay, some of the important terminologies. So we bring in work. Okay, so what is important is we need to find out the enthalpy. So what is the enthalpy point? So H1 is enthalpy at this point. So this is H1. So you bring. So this is enthalpy of 0.1, this is enthalpy of 0.2, and then this is enthalpy of 0.3 and 4. And then from the enthalpy value, we can get input work, which is the mass of refrigerant times the difference of the enthalpy, H2 minus H1. Okay, we have a terminology of heating effect, basically Q. C. It is a point. It is the move between 2 and 3 during the condensation. So key C is key condensation. So it's a H2 minus H3, and then we also have refrigeration effect. Refrigeration effect. Remember, we want to let go heat. Okay, that is QC. So the QR here. Okay, this is a refrigeration effect, which is H1 minus H4. Okay, that is the refrigeration cycles. Okay, here I will skip one. Okay, this is the basic cycle. So the basic cycle is this one. So you can always improve. For example, what I'm done. Okay, what we can do is actually we can improve. So what is done here, the improvement was done by adding one of the unit heat exchanger. Okay, so if you add, so this is new term. Normally we have 1, 2, 3, 4 point. So what happened now? So this is the original point. Okay, this is the original point. Okay, point 1. So this is our point 1. So point 1 is heated here. Okay, it's heated here. It means that now, so suppose point 1 is saturated vapor. So it's become point 1 accent. So this is superheated vapor. So how it is represented in the chart? It is from this point, it goes to the right because you are hitting it. When you hit it, you go to the right. Okay, and then it go the normal compression here. Okay, then now normally it's from 0.2 to 0.3. So this is the normal one. Number 3 is basically saturated liquid. And now because here 3, okay, what happened in 3 is you cool it down. So this part is cooling, another part is heating. When you cool it, you move to the left. So this is heating on the right, and this is cooling. Okay, so you see that when you have this heat, this kind of modification, you increase the performance. Okay, you increase the performance. For example, here, this is the basic cycle of refrigeration system. Okay, if I go carefully on this, okay, the refrigerant is 134. It's a 134A refrigerant. It's important. So we get a correct pH diagram. And we check point by point. This is point 1. Point 1 is 140 kilopascal. So, okay, that's the pressure. So this is 100 kilopascal. This is 200 kilopascal. So 140 is somewhere here. So this is point 1. Okay, and the condition here, if you look, it is saturated vapor. Saturated vapor is exactly on the line. Exactly on the line. It goes, okay, this is the adiabatic compressor. So basically, they are using the same line here, isentropic line. This they call it, this is adiabatic at point 2, so it's reached point 2 here, and point 2 pressure now is 1 megapascal. So this is 1 megapascal. Okay, the temperature is 60. How to get the temperature? We get the temperature from you look into this line of temperature. Okay, it goes here, go there 60. See it crossed that point. So this is 60. So there where you get it 60 degree Celsius, and then we condense it. When we condense, okay, P3 equal to P2. So the line must be straight, horizontal. And the condition is, we are given here 36. So we go there, and it's 36. This is 40. 40 is more or less the saturated. So 36 must be subcooled liquid. This is this one. So 3 is 36 subcooled liquid. And then it's throttle adiabatic. It bring it to the same pressure as P1. So it's go down to the same pressure as P1, which is 140 kilopascal. So this is how we translate the information from a basic layout of a refrigerator into the pH diagram, okay, pH chart. So now we have a condition where we add internal heat exchanger. Okay, remember when we do this one, so now point 1 is the same as the one before. This is point 1. So what happened is that we bring it to, because we heat it further, you have already vapor. Now you heat the vapor. So you bring the temperature, okay, from berapa ini? minus 22, you bring it up to the right, and it is to plus 20. So this is the condition now at 1x. And then we compress, instead of having at 0.2 before, now you have at 0.2x, and the temperature increased to 100 degrees Celsius. From 60 before, now increased to 100 degrees Celsius. And we bring it to the condenser, blah, 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 bang. In the condenser, okay, before it was saturated, subcooled liquid at 36 degrees Celsius, given here. And now, thanks to the heat exchanger, we bring it down further, okay, here to the left, okay, to the point of 3x. The temperature is cooled down to somewhere in between 20 and 0, probably around, it's not the middle, so it's not 10, probably around 12 degrees Celsius here at 3x. And then you go with the throttle. So all of the skill, so important skill in this concept is to be able to translate the given cycle to the pH diagram. Okay, and complicated problems can easily be solved if you know how to represent it using the pressure enthalpy diagram. I have a few slides left. There are many available refrigerant. Okay, but normally we choose the refrigerants based on three things: thermal properties, costs, and environmental impact. Okay, the freezing point, must be below the lowest temperature we want. We want a high latent heat. We want a low specific volume of the vapor, and then we want to have a high coefficient of performance. High coefficient of performance. Basically, all sum up here the properties of refrigerants with a high COP. Next, we think about costs, and lastly, we think about the environmental impact. These are these are the most example of how we consider choosing the refrigerant. And then the most popular I list here, it's a R. The most popular new refrigerant is R. They use code, yeah, and what I know is R22 is Freon. The rest I don't remember. This one dichloro something, I forget. So these are the most popular refrigerant now used in the US.